Assalamualaikum warahmatullahi wabarakatuh. Hi everyone. So in this video, we will teach you on how to solve problem related to doubles integral over non-rectangular regions. This is somehow the extension to what you have learned in topic 4.2, rectangular regions. So by the end of this video, you as a student should be able to sketch the non-rectangular region of integration, determine the limit of the double integral, evaluate the double integral, use double integral to find the volume of a solid and the area of the region, and last but not least, reverse the order of integration. Before this, in topic 4.2, we have introduced about type 1 and type 2 integral. So the same things will happen in topic 4.3. If you look carefully to what I have written over here with the module on page 234, by right you will see some changes according to the limit. So before this, in 4.2, when we discuss problem related to double integral of rectangular regions, the limits are given in terms of some constant value for both limits with respect to variable y, with respect to variable x. But when it comes to non-rectangular regions, one of the limit is written in terms of function instead of constant values. The reason why we call topic 4.2 as rectangular regions, when you try to illustrate the region R, you will see that you will end up with a rectangular shape, but it won't be happen in topic 4.3. That's why we call it as non-rectangular regions. Okay, the same thing as mentioned earlier will happen on topic 4.3, where you can always solve the problem either by using type 1 integral or by using type 2 integral. So without further delay, let's move to example 4.3. So in this example 4.3.1, the author asks you to evaluate the following double integral over region R, and the region R is given as a triangle bounded by these three situation or criteria such as x-axis, y-axis, and line 2y plus x is equal to 2. In topic 4.2, the limits with respect to variable y and x is very obvious in terms of it is written in terms of some constant values. But there is a tricky part when you try to solve problem related to non-rectangular region, where you have to be able to sketch the region R in two-dimensional coordinate system, and by sketching this region R, it will help you a lot in determining the limits for both variables. Okay, before we decide to solve the problem either by using type 1 or by using type 2, let's sketch the region R based on the description given in the question. As mentioned earlier, region R always lies in two-dimensional coordinate system. When we have two-dimensional coordinate system, we will have two axes, y-axis and x-axis. As mentioned by the author, this region R is bounded by x-axis. So here is your x-axis and this is your y-axis. And then try to sketch 2y plus x is equal to 2 by simply determine the x and y intercept. So in this case, what should I do? Okay, y intercept can be obtained by letting x is equal to 0, then you will have to y is equal to 2 and y is equal to 1. X intercept can be obtained by simply let y equal to 0, then you will get x is equal to 2. So this is y is equal to 1 and this is x is equal to 2. Therefore, this is a straight line, and this straight line is given by 2y plus x is equal to 2. Therefore, according to this description, I'll know that this is my region R. Okay. You can solve the problem either by using type 1 or by using type 2. Let me show to you one by one. We go to method 1, which is we will be using type 1 integral. So, when you have type 1 integral, you can transform this expression 2y plus x dA, then you can change it to dy dx. So I'll leave some space because I need to put the limits later. 2y plus x dy dx. So right now you have to look at the region R that you have sketched earlier. Okay, the region R will help you a lot in terms of determine the limits with respect to variable y and the limit with respect to variable x. So all I need to do on this region R, I have to sketch an arrow, and this arrow should be moving bottom up. So in this case, I sketch an arrow, and this arrow should be moving bottom up, and this arrow should be parallel to variable y or y-axis. Therefore, according to this arrow, the arrow will touch the blue line that lies on the x-axis first. Since right now we are talking about determining the limit with respect to variable y, y should be the subject of our equation, and the best equation to represent a line on x-axis is written as y equal to 0. Right after that, this arrow, right after it touch y is equal to 0, it will touch the red line, am I right? And this red line is given in terms of that equation, 2y plus x is equal to 2. What should I do with this equation? I should always remember in my mind that the upper limit of the first integral also belongs to variable y. Therefore, y should be the subject of your equation. So you have to do whatever it takes so that only variable y remain on the left hand side, and variable that is not related to y, you have to put it on the right hand side. I will get 2y is equal to 2 minus x, y is equal to 2 minus x divided by 2. Therefore, the upper limit of variable y is 2 minus x over 2. Right after that, what should I do with variable x? Lower and upper limit with respect to variable x can be determined by simply observing the region R. If you look carefully to this region R, x only start at x is equal to 0, and then it will end at x is equal to 2. Therefore, x is equal to 0 is the lower limit with respect to variable x, and x is equal to 2 is the upper limit with respect to variable x. So right after I manage to determine all the limits, now I can focus on solving this problem. And right now we are talking about partial definite integral, and this partial definite integral, when you try to integrate with respect to variable y, variables that's not related to variable y, you should treat it as a constant. Therefore, I believe I do something wrong over here. It shouldn't be 2y plus x. In fact, it should be the other way around, such as 2x plus y and 2x plus y. Okay, so right now I have to have 2xy plus y squared over 2 integrate, and then I'm going to evaluate from y equal to 0 until 2 minus x over 2. So when you try to solve the problem, you have to make up your mind. Do not get confused easily. So right now, all of these values should be substituted into variable y, because before this we integrate with respect to variable y. So I should get 2x 2 minus x divided by 2 plus 1 over 2 2 minus x over 2 squared minus 2x times 0 plus y, not y, 0 squared over 2. So I believe this term all the way 0. Now we can focus on simplify this portion. So in this case, I will get 2x minus x squared plus 1 over 2 1 over 4. Now I will try to expand 2 minus x times 2 minus x. I should get 4 minus 2x and then minus 2x plus x squared. Okay, and then right after that, 2x minus x squared plus 1 over 8, 4 minus 4x plus x squared, and then I will get 2x minus x squared plus 1 over 2 minus x over 2 plus x squared over 8. Then I will get 1 over 2 plus 3x over 2 minus 7x squared over 8. Then integrate from x equal to 0 until 2 with respect to variable x, and then I will get 1 over 2x plus 3x squared over 4 minus 7x cubed over 24, and then I'm going to evaluate from x is equal to 0 until 2. Therefore, I will get exactly like the answer in the module, which is 5 over 3. And then I have mentioned earlier, we can always solve this problem by using two methods, either by using type 1 integral or by using type 2 integral. So right now, let's us focus on solving this problem by using method 2, which is by using type 2 integral. Okay, so right now, when I have type 2 integral, this double integral over region R for 2x plus y with respect to a can be written as 2x plus y dx dy. Okay, so I leave some space over here because I want to put the value for the limit letter. Okay, so let me copy the figure that we have sketched together earlier. Okay. 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 So right now, when you decide to solve the problem by using type 2 integrals, so instead of sketching an arrow bottom up and this arrow parallel to y-axis, so right now, if you have type 2 integral, you have to sketch an arrow, and this arrow should be moving from left to the right, and this arrow also parallel to x-axis. Okay, Right after that, according to this black arrow will touch a line, and this blue lines lies on y-axis, and the best equation to represent a line on y-axis is as simple as x is equal to 0. Remember, when we want to determine limits with respect to variable x should be the subject of your equation, not the other way around. So right now, if you look carefully to what you have over here, this black arrow, it will touch the red straight line or the red line, and the red line is given by this expression such as 2y plus x is equal to 2. But you have to remember, the upper limit also should be written in terms of variable x, which is x should be the subject of your equation. By doing something on the expression given to us, and at the same time you have to make sure x is the subject of your equation. Therefore 2 minus 2y should be the upper limit with respect to variable x. And what should I do when I try to determine lower and upper limit with respect to variable y? I have to observe this region R and look carefully on y-axis, and then try to observe y start at y equal to 0, and then it will end at y is equal to 1. Therefore, by using these limits, now you can solve the problem, and trust me, the answer will be equal, which is 5/3. So I leave it for you to explore on your own. So let's move on to the next example. For single integration, normally we will use it to determine area under the curve. By using double integral, we can determine the area of the region R, and at the same time we can also use double integral to determine the volume of a solid bounded by a function. Now let me write something. So this is the formula to determine the volume, which is the volume can be determined by using double integral over region R, and then for function fxy with respect to a, and again the a can be expanded to either type 1 or type 2 integral. This one is for volume of a solid. Meanwhile, we can also use double integral to determine the area of the region R. Therefore, the area of the region R can be determined by using double integral over region R dA, and at this time, your function fxy, you can assume it to be 1, because you can relate it with the topic that you have discussed in 4.1. Basically, the function has been embedded into one of the integral of this double integral. Okay, you have to pay more attention towards the question given to you. Either the question asks you to determine the volume of the solid or determine the area of the region R. If the question asks you to determine the volume of the solid, you have to determine what is the function fxy or what is function z. Meanwhile, when the question asks you to determine the area of the region R, you can always assume the function fxy equal to 1. So if you try to get an idea on how this works, maybe you can try to look back at single integration involving polar coordinates or rectangular coordinates. So let's take a look at the next example. Example 4.3.1.1. So in this question, ask you to determine the area of the region enclosed by the parabolas y is equal to x squared and y squared is equal to x. So right now the function is not given. When the function is not given, and at the same time the question has been described that you have to determine the area of the region R. Therefore, we are talking about area of the region R by using double integrals. So let us recall the correct formula. So this is the correct formula, such as double integral over region R with respect to A. So right now, it's up to you to solve the problem by using type 1 or by using type 2 integral. So maybe we can try to approach this question by using those two methods. So right now, what should I do? I should do something with the region R. As mentioned earlier, when it comes to double integral onwards, you have to be able to sketch the region R, because by sketching the region R, it will help you a lot to determine the limits for both variables. So in this case, let us sketch the region R based on the description given in the question. So you have to always bear in your mind the region R always lies in two-dimensional coordinate system that involve y versus x-axis. So what should I do with this question? I have to look back at the question given to me, which is the region R consists of y is equal to x squared and y squared is equal to x. So right now, I know that y is equal to x will give me a small shaped graph. Meanwhile, x is equal to y squared will give me C-shaped parabola. So when you heard the word enclosed, by right, we are talking about common region based on these two curves. So right after that, I should be able to sketch or shade the region R. And then I'm going to write it as region R. So this region R will help you a lot when it comes to you try to determine the limits. So right now I'm going to cut or copy this figure because it will help me when I try to determine the limit by using both methods. So right now, let me write down or sketch these two tables. Okay, these two tables indicate that you can solve the problem either by using type 1 or by using type 2. So let us use method 1 and method 2. Okay, so right now we have to assume function fxy equal to 1. So for method 1, area of region R is equal to the double integral over R over region R dA, and then when I expand dA, I will get double integral. I'm going to leave some space dy dx. Okay, when I have this question, so I think right after this I don't have to solve each and every question, so I will leave it for you to discover on your own, but we try to discuss in terms of how to determine the limits, because the knowledge of integration we assume you have possessed during the calculus subject. So right now I'm going to paste the curve that we have sketched together earlier. Again, what should I do? I have to sketch an arrow, and this arrow should be parallel to y, and then it always start bottom up. So this is my arrow. So right now I have to know that the blue curve is represented by y is equal to x squared, and the green parabola or green curve is represented by x is equal to y squared. Therefore, right now, according to this red arrow will touch the blue curve first, and the blue curve is represented by that equation y is equal to x squared. Since we have up to solve the problem by using type 1 integral, the first integral will be in terms of or with respect to variable y, and y should be the subject of your equation. So when I have this type of question, I have to have y is equal to x squared, and x squared should be the lower limit with respect to variable y. So right now, what should I do? I have to look at the red curve or red arrow that I have sketched earlier, and then right after the red arrow touch the blue parabola, it will touch the green parabola, and the green parabola is represented by that equation x is equal to y squared. So right now I have to make sure y is the subject of your equation. Right now, what should I do? I have to have y is equal to plus minus set x. Basically, this green arrow has been divided into two separate regions, either in type 1 and not type 1, which is in quadrant 1 and quadrant 4. Right now we are talking about a portion of parabola that lies at the first quadrant, and the best equation to represent the part of parabola that lies in the first quadrant is y is equal to positive set x. Therefore, set x will be the upper limit with respect to variable y. What should I do right after this? To determine the limits with respect to variable x, I have to observe the region R. So right now, if you look carefully, these two curves eventually they meet at 2 points. The first one, obviously, they meet at origin, then they meet somewhere here. So right now we have to solve this problem simultaneously in order to determine the point of intersection. So solve y is equal to x squared and x is equal to y squared simultaneously. So what should I do if I try to solve this problem simultaneously? You will see that I will have x is equal to x to the power 2. I will get x equal to x to the power of 4. X to the power of 4 minus x is equal to 0. X times x cubed minus 1 equal to 0. X is equal to 0, and x cubed equal to 1. X is equal to 1. Therefore, the value here is x is equal to 1. And the lower and upper limit with respect to variable x is as simple as x is equal to 0 and x is equal to 1. So I hope you can see the process. So why don't we try to repeat the same process, but right now we will use method 2. Again, if you want to use method 2, the function f x y again is equal to 1, because right now we are talking about the area of the region R. So right now I will have function f x y is equal to 1, and the formula to determine the area by using double integral is double integral over region R dA. So right now I leave some space here, then I will have dx dy instead of dy dx. Then okay, I'm going to use the same figure because right now this is our region R. And then I'm going to sketch an arrow, but this time around, since we have decided to solve the problem by using type 2 integral, you have dx dy, so you have to sketch an arrow, and this arrow should be parallel to x axis, and at the same time it always travel from left to the right. So you see that this is my arrow. So based on this arrow, I know that this red arrow will touch the green parabola first, and since right now we have dx dy instead of dy dx, so the first integral is actually integration with respect to variable x, and variable x should be the subject of your equation. So we know already that this is x is equal to y squared, meanwhile this is y is equal to x squared. Right now, the lower limit with respect to variable x can be represented by that x is equal to y squared. And right after the red arrow touch the green parabola, it will touch the blue parabola. So when the arrow touch the blue parabola, and the blue parabola is represented by y is equal to x squared. And at the same time, the first integral is actually integration with respect to variable x. So what should I do right after this? I have to let x, and I have to make sure x is the subject of my equation by removing the squared notation. So I will have x is equal to plus minus z y. Since our blue curve is divided in the first and second quadrant, and we are talking about a portion of parabola that lies on the first quadrant, and the best equation to represent a portion of parabola on the first quadrant is actually z positive y. Therefore, what should I do right after this? I have to determine limit with respect to variable y. So right now, by using the first method, since we are able to solve the equation simultaneously to determine the point of intersection, such that we know that it will intersect at x equal to 0 and at x is equal to 1. So since we are talking about point of intersection, you can use either equation of the parabolas to determine the value for variable y or y coordinate. So when x is equal to 0, y is equal to 0 squared, which is 0. When x is equal to 1, y is equal to 1 squared is equal to 1. Therefore, the value here is 1. To determine limit with respect to variable y, all you have to do is by observing the region R. And this time around, the lower and upper limit with respect to variable y is actually y is equal to 0, and 1 will be the upper limit with respect to variable y. So if you solve the problem, you by right should have the same answers, which is area of the region R is equal to 1 over 3. By using either method, it will give you the same answer. So I don't think that I have time to explain all the calculations, so I really hope you have the ideas on how to solve this problem. Remember, we are talking about partial definite integral, so you have to recall back what you have learned in topic 4.1. Okay, so let's take a look at the next example. So this example 4, let me write down first. Example 4.3.1.2. This example, we are talking about the usage of double integral to determine the area of the solid. So right now, you have to remember, when we use double integral to determine the area or to determine the volume, you have to determine what is function z or what is your function fxy. So right now, in this case, your function fxy is given as x plus 2y plus z. No, this is not the answer. Okay, wait for a while. Okay, so right now, when you have this type of problem to determine the volume, so you have to recall the correct formula first. So the volume by using double integral can be determined by using this formula, such as double integral over region R for function fxy with respect to a. Again, you can solve this problem either by using type 1 or by using type 2 integral, or method 1 or method 2. So I will try to show you both methods. So right now, when you have this kind of question, what should I do? I have to determine my function fxy first. So let me write something. Okay, how to solve. Okay, so right now you have to determine your function fxy. Your function fxy is actually a function of z written in terms of variable x and variable y. Right now, they are talking about to determine the volume of the solid bounded by all coordinate planes such as xy plane, yz plane and xz plane, and at the same time x plus 2y plus z is equal to 2. So right now, since you have that equation, you can always let z as the subject of your equation. You will get 2 minus x minus 2y. 2 minus x minus 2y will be the function fxy equal to z. And what should I do right after this? Right after I manage to determine the function written in terms of variable x and y, what should I do? I have to sketch the region R. But when you try to sketch the region R, the description is given in terms of volume in terms of solid in 3-dimensional coordinate system. So if you look carefully on page 237, the authors sketching the graph in 3D that involves z, y and x. And then, okay, so right now you have this equation z plus x plus 2y equal to 2. So by determining the x, y and z intercept, you are able to sketch the plane, yeah? So right now z is equal to 2, x is equal to 2 and y is equal to 1. So this is your plane in 3D, and don't forget it will lies in the first octane only because it is bounded by all coordinate planes such as xy plane, yz plane and xz plane. So when we try to determine the volume by using double integral, you have to remember you have to be able to determine where the region are, and always remember region R always lies in 2-dimensional coordinate system. So if you look carefully to the solid that you have sketched based on the description given in the question, all we can do now is that we have to be able to project the surface in 3D into 2-dimensional coordinate system so that we are able to determine the limits with respect to variable x, y. So right now, okay, this is your region R. Okay, so since that is your region R, I'm going to transform it in 2-dimensional coordinate system that involve y and x. So this is y, this is x, and the value here is 1, right? So 1 and 2. Okay. And this is your region. So this is your region R. What should I do with this region R? Again, you can solve it by using type 1 or type 2 integral. Either method will give you the same answer. Method 1 and method 2. Again, I'm going to copy whatever I have over here. Okay, what should I do now? So remember the formula. V is equal to double integral over region R for function fxy dA. So I will have double integral since that is my function z, such as 2 minus x minus 2y dy dx. Okay. Okay, again, this is my region R, and then I'm going to sketch an arrow bottom up parallel to y-axis. Then the first integral is integration with respect to variable y, and y should be the subject of your equation. And the best equation to represent this purple straight line is by assuming z equal to 0, you will get x plus 2y equal to 2. Okay, so right now, what should I do? The lower limit, if you look carefully on this red arrow, it will touch the black line that lies on x-axis, and the best equation to represent any line that lies on the x-axis is y equal to 0. Right after that, it will touch the purple curve, and the purple curve is represented by this equation, and it can be rewritten in terms of y as the subject of your equation, such as 2 minus x, y equal to 2 minus x over 2. Therefore, it will be the upper limit with respect to variable y. And then what should I do right after this? I have to observe along x-axis to determine limits with respect to variable x as long as it covers the region R. Therefore, the second integral is integration with respect to variable x. Therefore, x should be the subject of my equation. And then you will see that it starts at x is equal to 0, and then it ends at x is equal to 2. Therefore, 0, 2 is or are the limits of variable x. Okay, so let's move to method 2. Again, recall the formula such as v is equal to double integral over region R for function fxy dA. So right now I will have double integral, and the function is written as 2 minus x minus 2y dx dy. So again, I'm going to sketch the region R. Okay, so based on this region R, I have to sketch an arrow, and this arrow should be parallel to x-axis from left to the right. So based on this arrow, I know that this equation can be written as x plus 2y equal to 2. Therefore, this red arrow, the red arrow touch the first curve on y-axis, and the curve on y-axis can be represented as x is equal to 0, and then it will touch the purple curve, and the purple curve or purple line can be represented by that equation, such as x plus 2y is equal to 2, and x should be the subject of equation x is equal to 2 minus 2y. Therefore, 2 minus 2y is the upper limit with respect to variable x. So right now, what should I do right after this? I have to determine limit with respect to variable y. So I have to observe this region R, and then according to my observation, y starting from y is equal to 0, then it ends at y is equal to 1. So 1 is the upper limit with respect to variable y. So by using either method, you will end up with the same answer, such as v is equal to 2 over 3. Again, I don't think that I have time to show to you the solution one by one, but I need you to have the ideas to determine the limits, because if you don't have any idea to compute the limits, it will be quite difficult for you to understand the rest of the process, because I believe the rest of the process depends on your basic knowledge for partial definite integral, and also basic rules when it comes to basic integration. Now let's discuss this example 4.3.1.3. Again, if you look at the question given, by right, the author asks you to determine the volume by using double integral. So right now, when you have this kind of problem, please recall the correct formula to solve this problem. The volume can be determined by using this formula, double integral over region R for function fxy dA. So we will try to discuss on how to solve this problem by using those two methods that have been mentioned earlier. And right now, the question asks you to determine the volume that lies under the parabola. So that is the keyword. The function has been given to you, such as z is equal to x squared plus y squared is actually function fxy. So sorry, I forgot to write something. How to solve. Okay, so right now you know already what is your function fxy. Right after this, what should we do? Yes, you are correct if you are thinking about to sketch the region R. Again, this region R always lies in two-dimensional coordinate system that involve y and x axis. So here comes the second part of the information in the question, such as region R is explained as a region bounded by xy plane and at the same time bounded by two curves, which is the straight line y is equal to 2x and the parabola y is equal to x squared. So again, I'm going to use a different color to illustrate different curve, which is y is equal to x squared. So this is equation y is equal to 2x, y is equal to 2x and y is equal to x squared. Again, the keyword here is region R bounded by these three criteria or these three conditions, such as xy plane, y is equal to 2x and y is equal to x squared. Therefore, this is your region R. So right after we manage to sketch the region R, what should we do? We have to make up our mind whether to solve this problem by using type 1 integral or by using type 2 integral. So for exercises purposes, I'm going to show you both methods to solve this problem, which is method 1 and method 2. Okay, right after this, what should I do? Again, I'm going to write down the formula, which is v is equal to double integral. Again, the function is x squared plus y squared. Method 1 represent type 1 integral, which is dy dx. Okay, so when I have this type of equation, what should I do? Okay, let me copy first. Okay, I need to sketch an arrow, and this arrow should be parallel to y-axis bottom up. Okay, so based on my observation, the red arrow will touch the parabola first, and this parabola is represented by equation y is equal to x squared, and then right after that it will touch the green curve, which is y is equal to 2x. Therefore 2x will be the upper limit in terms of variable y. So what should I do right after this? I have to observe along the x-axis. So in this case, based on your observation, they will intersect at x is equal to 0 and another value of x. So right now I have to solve these two equations simultaneously, such as x squared equal to 2x, x squared minus 2x equal to 0, and x times x minus 2 equal to 0. And the answer will be x equal to 0 and x equal to 2. Therefore, the value here is x is equal to 2, and the best lower and upper limit with respect to variable x is actually x equal to 0 until x is equal to 2. So that's how you solve this problem by using type 1 integral. So right now what should I do? I have to solve this question by using type 2 integral. So I'm going to have v is equal to double integral. So let me put some space. Double integral x squared plus y squared. So instead of dy dx, we will have dx dy. So I'll paste the curve here. Again, I'm going to sketch an arrow, and this arrow should be parallel to x-axis from left to the right. So according to my understanding, according to my understanding, in order to determine the lower and upper limit with respect to variable x, I should follow the red arrow. So right now, according to my sketching over here, the first integral is actually integration with respect to variable x, and x should be the subject of my equation. Therefore, I will get from here x equal to y over 2. Therefore, y over 2 will be the lower limit when I try to determine or solve this problem by using type 2 integral, which is based on this red arrow. It will touch the green line first, and then it will touch the purple curve, which is the parabola, and the parabola is represented by y is equal to x squared, and again x should be the subject of equation. You will get, wait for a while, x is equal to plus minus z y. Right now you have plus minus z y, so whatever you have on the right hand side, we will have positive z y, and whatever parabola you have on the second quadrant, we will have negative z y. So in this case, you will have z y as the upper limit with respect to variable y. So what should I do right after this? Since in method 1, I know that it will intersect at coordinate x is equal to 1, x is equal to 2. So by using the formula, by using either equation, you will get the same y coordinate. So when x equal to 2, y is equal to 2 squared, which is 4. So the value here is 4. So according to my observation, this region R, it will occupy y is equal to 0 and y is equal to 4. So 4 will be the upper limit with respect to variable y. So if you try to solve this problem by using either method, you will end up with the same answer, which is, for this case, okay, let me do something over here, which in this case I will get v is equal to 216 over 35. So due to time constraint, I will help you in terms of determining the limits with respect to variable x, with respect to variable y. I will allow you to explore on your own on how to solve the rest of the problems. So let's meet again in another video. Bye.